Okay, welcome everybody to this second seminar in our causality series. 3 weeks ago now we had Clément presenting, and we had to cancel one last week, so sorry about that. That was affected due to the strike action. That's been rescheduled to April 6th, and the Eventbrite page has been updated. You can now register for that. You will need to re-register, so if you registered for last week's session, I don't think we've been able to transfer those registrations, and we probably wouldn't anyway, because we don't know that you're available on April 6th. But if you wanted to attend that one, please do register and tell your friends, because we're very happy to host this, as widely as possible. So welcome everybody to this Causality Seminar Series. It's organized by the Institute of Data Science and Artificial Intelligence. And I said this at the start of the previous seminar as well, but we're going to repeat it. The really great thing about this institute is that it is cross-cutting, and it means that we have people from the social sciences, from philosophy, from economics, stats, maths, computer science, all sorts of disciplines. And it's really interesting how those different disciplines approach the simple enough question of causality. And it has been absolutely fascinating to watch these paradigms colliding in these seminar series, because there's whole fields of work that have been developed. And it's not my experience that these fields talk to each other a huge amount. And it has been really interesting to date to have different people from different backgrounds talking. I mentioned to Kate previously, we have had huge interest, and that's why we have almost 70 people in the room at the moment. There's no particular housekeeping except to say that we have had a few people who do not want to be filmed. So our way around this, our simple way around this, is that we'll record Kate's talk, but as soon as she stops, we will stop recording questions, and that means we don't need to edit any of the videos. So if you could hold your questions until the end, that would be fantastic. So Kate Tilling, I know Kate it must be coming on for about 20 years now through the Society for Social Medicine. And she is just an absolutely inspirational statistician, has been working at the coal face of epidemiology for as long as I've known her, doing the foundational work to improve research practices in that field. I think, we can all agree that citation counting is icky. But if you do look up Kate on Google Scholar, you will see this exponential increase from a high base of her work. And I think it's really encouraging. And I think it reflects not only the standard of her output, but a growing awareness that we need to engage with these issues of causality. And Kate does a lot of work in longitudinal research as well. And I just find it really, it's good news that a methodologist like that is having this increasing profile. And it is really, truly extraordinary. I remember about 15 years ago, I attended a mediation analysis seminar that Kate ran with the Society for Social Medicine. And I remember a pompous guy at the end of it. So Kate was telling everybody about how we need to take take mediation analysis more seriously and go beyond the Barron and Kenny approach. And this guy said something like, well, nobody does the Barron and Kenny approach anymore. And that was 15 years ago. And whenever I see the Barron and Kenny approach still applied, I think of Kate, because it's still, there is still a huge amount of work to do. Anyway, I won't take up any more of Kate's time. Over to Kate for our seminar today.
Great. Thanks very much, Mark, and for inviting me. Is that showing the right thing? That's brilliant. Okay, yes, so yeah, thanks very much for inviting me. Nice to see all your names, even if I can't see any faces in the room. Yeah, I kind of feel I've got quite a lot to live up to now, but I'll do my best. So basically this talk is kind of a amalgam of various things I've been involved with at the interface of selection bias and missing data and their impact on causal inference. So I'm just going to talk very briefly about what I mean by causal inference for this talk. I appreciate that most of you will know what directed acyclic graphs are, but I've just got 3 slides that you can sleep through if you do, just to make sure everybody's on the right page, because I use them quite a lot in the rest of the presentation. And then I'm going to talk about missing data and its impact on conclusions using various different analyses. Talk about selection bias and also index event bias, where we're studying prognosis in cases only. And as I said, this is work compiled from various things I've been involved with over a distressingly large amount of time. And these are all the people who I've worked with or who've led some of this work. They've all given permission for me to present it today. Most are from Bristol, but Jess Tyrrell from Exeter, Osama Mahmood, who's now at Essex, and Frank Dudbridge from Leicester. Okay, so to start with, what we're talking about causal inference. So what I'm thinking is a common aim of medical research is to find out whether X causes Y. I'm not going to go into the philosophical discussions of what we mean by that. I'm leaving that for people like Miguel Hernan, who does it beautifully, but I'm kind of assuming we can all have our own definition of what we mean by X causing Y. And then you define the outcome Y, IX, individual I, if you set their exposure equal to a given value X. So for example, if X can take value 1 if you're treated, or 0 if you're untreated, you can define what the outcome would be for individual I if they were treated, and what the outcome would be for individual I if they're not treated. And then you define the cause effect of treatment versus no treatment for individual I if their outcome if they were treated is not the same as their outcome if they were not treated, and estimate it by the difference between those two. And obviously this is called a counterfactual or potential outcome, because usually we can only observe one of those two outcomes for any given individual. What I should probably go back to, what I'm not going to do is talk about sort of complex stats methods for estimating causality under various different assumptions. So it's not sort of G estimation or marginal structural models or any of the sort of more exciting things. I'm kind of assuming here that we're just looking at do we know whether X causes Y? So a relatively simple causal structure. Okay, so then I'm just going to briefly talk about directed acyclic graphs. So there's an example shown here where we've got our X, which I'm hoping in all of my talk I've been consistent, and X is my exposure and Y is my outcome. And either C or U are confounders. And the key thing about DAGs is, firstly, they've got directed edges, which are the arrows here linking the variables. And an arrow from X to Y shows that X causes Y. They're acyclic because you can't get back to the place you started from. So if you start from X, you can't follow a load of arrows and get back to X. They're graphs because they're graphs, and they're supported by a lot of mathematical theory, in particular, obviously lovely papers by Judea Pearl's group. So using the acyclic graphs, there's kind of 3 ways that X and Y can be associated in my data. Either X causes Y, or we've got a common cause of X and Y, which is shown here by our C with an arrow to X and an arrow to Y. So here you would see that X and Y were associated, but it's just because C causes both of them. Or, and the one that's important for all of the talk today, is if you condition on a common effect of X and Y, then X and Y will be related in at least one stratum of S. And this is often called collider bias. It's called selection bias, but they aren't the same thing. So I think it's collider bias because X and Y, their arrows are colliding at S. And an example here is if you have, for example, IQ and athletic ability being independent in the general population, and then you've got a school that has a selective entrance exam and a load of sports scholarships. If you go into the yard of that school, you're liable to find that the people who are really good at sports maybe were slightly less good at passing entrance exams, and vice versa. Whereas in the general population, they're not related at all. So yeah, the key thing for selection bias and missing data is that if you condition on a common effect of X and Y, you will tend to induce bias. Doesn't always happen, but you will tend to. Okay. So then thinking about DAGs and their use for causal analyses, I guess I'm still thinking of this very simple scenario where I want to see whether X causes Y. And the idea often is to condition on a set of variables, C, such that if you see that X and Y are associated in your data set, the only or the most plausible reason is that X causes Y. I'm not thinking here at all about reverse causation. So I'm assuming that you do know for some reason that actually Y doesn't cause X. And maybe that's something to rethink at the end. But that's what I'm assuming here, that you if you condition here on all the C's, then we can identify the causal effect of X on Y. So that's the no unmeasured confounders assumption. And we can do that just, if we want to, just using standard regression. Now, obviously, the no unmeasured confounders is often a pretty implausible assumption. I mean, I work almost universally in observational epidemiology. So we allow people to choose their exposure, or a doctor chooses it for them, or their parent chooses it, their child, etc. So there's a whole load of factors here, I've called them U for probably unmeasured, that affect the exposure of a given individual. And then we allow them to sort of proceed uninterfered with, and their Y happens or doesn't happen. So there's possibly bazillions of tiny things that affect both X and Y. So assuming that you know them, or you've measured them all, and you've measured them all without error, is usually somewhat implausible. So the other kind of analysis I'm going to focus on today, partly because it's one we use a lot in the IEU, and partly because it's quite useful for this no unmeasured confounders assumption, is an instrumental variables analysis. So here we've got a new variable Z, which is an instrument for the effect of X on Y if it is associated with X, it's not associated with U, and it's not associated with Y except via X. And under those assumptions, then you can kind of see from this DAG that you can only see an association between Z and Y if this arrow here exists. So providing that this arrow here exists, which is the assumption above, then you only see an association between Z and Y if X causes Y. And then with the addition of one of several flavors of a fourth assumption, you can then actually estimate the effect of X on Y using this instrumental variable. And one commonly used instrumental variable, I guess, in our field is Mendelian randomization, where the Z is genetic information. So yes, commonly used instruments include policy changes, and the one example that I really work through in this talk uses raising of the school leaving age as an instrument. Or, like I just said, genetics, working on the principle that alleles are randomly allocated at birth, or random allocation in a randomized controlled trial. So then the main focus is talking about selection bias, and it is often collider bias, but not always. I'm only going to talk about when selection causes bias due to colliding, but there's a lot of other situations when it doesn't happen via the colliding mechanism. So this is kind of a subset of selection bias, if you like. And the sort of umbrella selection bias I'm thinking of as being caused by missing data. So people who are missing one bit of a questionnaire, or who missed out one whole questionnaire out of a series, drop out. So they were in a study up to a certain point, and then they moved away, they emigrated, they decided they weren't interested anymore, so they dropped out after that. One that I've been particularly interested in is selection into a study. And that one's kind of interesting, partly because it's often forgotten about, and partly because it's much harder to study. When you've got dropout or missing data, you do at least have some information on the people who have dropped out or who have some information missing. And crucially, you know how many of them there are. Whereas selection into a study, you tend not to know necessarily how many people never turned up, or how many people weren't asked. And then lastly, one that we've been focusing on quite a lot over the last couple of years is studying only a subgroup. So for example, looking at prognosis from a disease, you have to only study people with that disease. So you've kind of selected people who've got the disease, and that can cause issues. So as we said before, if two unrelated factors cause selection, then they will likely be associated in the selected cases. So this is all about collider bias. Now I'm just going to go through, I think it's about 5 slides with very similar looking DAGs on each one, and talk about different selection mechanisms and how they might affect a linear regression analysis where you're just regressing Y on X with or without some confounders, and an instrumental variable analysis. So we're considering this sort of scenario. So we've got a valid IV for X. We're looking to see whether X causes Y, and we've got some confounders which may or may not be measured. So again, a very simple scenario, and obviously the more complicated you make this, the harder it is to draw firm conclusions. So at the moment, I'm just sticking to this very simple scenario. So the one, I don't know why I put this one first, the one I think is most interesting in a way is if the selection depends on the exposure. So if you're looking for the effect of, say, body mass index on later cardiovascular health, so X is your body mass index in midlife, Y is your later cardiovascular health, U is absolutely shed loads of stuff, including socioeconomics and lots and lots of lifestyle characteristics, etc. And then IV could, in this instance, be a genetic instrument for body mass index. So then the idea is to say, does body mass index cause later cardiovascular outcomes? And it might be that if you have a greater body mass index in midlife, you might be less likely to be in the study and have later and have your cardiovascular outcomes measured. You might even be less likely to be in the study in the first place. That might be due to other ill health, because increased body mass index will cause you to have other health problems, and that might cause you not to be in this study, or it might cause you to drop out of the study. So here we're saying we've got this study, and at some point body mass index causes selection. So you're conditioning on selection, which is has the same effect as conditioning on X, and therefore induces a path between your instrument and U. So what happens then is that your straightforward regression analysis of Y on X isn't biased by this problem. So the fact that the people with a higher body mass index have dropped out of the study doesn't matter for the regression of Y on X. It's obviously biased by confounding, but if you adjust for U, then you're fine. So your causal analysis there will be unbiased, even in the selected sample, provided you adjust for U. But your instrumental variable analysis is biased, because the bit of the instrumental variable analysis where you regress Y on IV, you've got the path from the IV to X to Y, but you've also now got a path from IV to U to Y. So again, unless you also adjust for the U's, which then kind of negates the point of doing the instrumental variable analysis in the first place, you're now got a bias due to selection in your instrumental variable analysis. I think it's also pretty common that selection will depend on the unmeasured or the measured confounders. That doesn't cause any bias with the instrumental variable analysis, because the instrumental variable analysis doesn't have any concern with the confounders. It will bias the simple regression analysis unless you adjust for U. If U is unmeasured confounders, then in some ways the selection actually helps. It moves some of the bias due to confounding. And you can kind of think of this as if that was, I don't know, education was confounding X and Y, and you restricted it only to people who have been educated to degree level. You're kind of getting rid of a lot of that confounding, because you are essentially at its extreme stratifying on the confounder. So in a weird sort of way, if selection depends on the confounders, it can actually unbias a bit a standard regression analysis. if selection depends on the instrument and the unmeasured confounder. And I think this is a bit of a weird one, because our assumption in general with the instrumental variable analysis is that the instrument kind of has very direct effects, if you like, on X. So it's a little bit odd for the instrument to be affecting selection not via the X that you're interested in, but it can do. And in that case, you can see you've opened a path between the instrument and the U, and again, that will bias your instrumental variable analysis. And your linear regression will be biased unless you adjust for U. So here, selection depends on the outcome, which is why if in truth there's no effect of X on Y, then this won't cause any bias. So you won't get bias under the null, which I think is quite important, because often we are sort of first and foremost interested in, is there a causal effect or not? And then after that, in how big is the causal effect? So if there really isn't an association, if really X does not cause Y, then if Y affects your selection, that won't bias anything. But if there is a causal effect and you select people based on their outcome, then you will get bias. And the exception to this, obviously, is if you've got a case control study and you use logistic regression, which has a weird robustness all of its own to this. Okay, last one. Again, I think this one's quite a nice one, because and also very plausible. So what we've got here is a cause U1 just causes X and U2 just causes Y. And so your normal regression analysis doesn't have bias because there isn't any confounding. But if both those two variables cause selection, then your selection has kind of induced confounding, and therefore you will get bias of the normal linear regression analysis, but not the instrumental variable analysis. And this one again seems potentially quite plausible. Yeah, and will cause bias in at least one of the kinds of causal analyses you might think of doing. Okay, so that's the end of the sort of various different DAGs, which I just kind of think is interesting to think how a given selection mechanism might affect the analysis you want to do. And in particular, drawing out the DAG of your causal question and what might affect selection can help either to choose which kind of analysis method you might want to use, or to think what the comparison of the two might tell you. Because you're never going to be, well, you're unlikely to be really sure exactly what the selection mechanism is, especially if it's selection into a study where you really don't know what the missing people are like. But if you've got a couple of different plausible selection mechanisms, and you can start then to disentangle which analyses will be unbiased or less biased under those different plausible mechanisms, then sensitivity analyses become more directed and the comparisons make more sense, I think. So I'm just going to present a couple of slides now from a paper that Rachel Hughes led, which is about selection bias specifically in instrumental variable analyses. So here we've got the same setup as before, except we've divided the confounders into known confounders that you can adjust for and unknown confounders that you can't. I'm just going to present one slide of simulation results, which is this one, and then an applied example. So this slide, the two axes, you've got sort of an axis on the left and an axis on the right. The one on the left is the coverage of the confidence intervals, and then one on the right is the standardized bias of the causal estimate. The dotted line at the top is nominal coverage for the left and unbiased for the right. And then the x-axis shows what the selection depends on. So you've got nothing, where everything should be unbiased and nominal, and gratifyingly it was. Selection just depends on Z, selection depends on Z and the measured confounders, just X, etc. And then just to add in more complication, we have a moderate instrument and a strong instrument. So this kind of backs up what some of the results in the previous discussions of directed acyclic graphs. So basically, if selection depends on either nothing or just said you don't get bias and you do get nominal coverage. Everything else you get some bias and therefore some under coverage. The coverage is always better for the moderate than the strong instrument, and that's largely due to standard errors, not due to bias, and that's kind of why we've shown them both here. So you can see that the bias is less for the moderate than the strong instrument here, but the coverage is better for the moderate than the strong instrument because the standard errors are a lot wider. But basically, yeah, everything here is biased to some degree. The moderate instruments on the whole are less biased than the strong instrument results, and particularly if selection depends on the instrument and the outcome, in which case we were down to pretty much no coverage for the strong instrument, for the moderate instrument, and a lot of bias. So we wanted to look at this in a practical example. So we looked at education and smoking in UK Biobank. So we're wanting to say, what was the effect of an extra year's education on the decision to take up smoking? We think it's pretty unlikely that we can measure all the confounders that relate to your continuing education and your decision to smoke. So we wanted to do that. The analysis of choice was an instrumental variable analysis. And rather than using genetic instruments for education, here we were using the raising of the school leaving age policy as an instrument. So restricting to, although it says 500,000 participants there from UK Biobank, we restricted it to the participants who were born 1 year either side of the cutoff that would have put them in the policy reform that raised school leaving age from 15 to 16 years. So one group of people left school if they wanted to at 15, and then the other group couldn't leave until they were 16. Now this table shows we did a standard linear regression at the top and instrumental variables at the bottom. And we did them both complete case and using inverse probability weighting. So the weighting was designed, here we think that education causes selection into biobank. If you compare UK Biobank with the sort of census level data on the UK, there are higher levels of education in UK Biobank. And so we use that census information to get weights for people being in UK Biobank according to their education. It's obviously wildly simplistic because we're assuming that smoking doesn't affect being in UK Biobank, but we kind of got around this because this was a methodology paper and we were just showing an application. So it doesn't have to be completely plausible. Okay, so taking that with a pinch of salt, the weighted is using, population level data to weight up for the education. So what you can see is for the regression analyses, nothing changes. And that's because of what I showed right at the beginning, which is that missingness depends on the exposure. It doesn't bias the standard regression analyses. Okay? So they don't change. And what they both say is that an increasing year of education leads to a 20% reduction in your chance of being an ever smoker and a 14% reduction in your chance of being a current smoker. For the instrumental variables analysis, which is affected by this education causing selection problem, the complete case analyses were essentially showed that there could be either a benefit or a harm to increased levels of education. And with estimates that were slightly negative for ever smoking and slightly positive for current smoking, but with wide confidence intervals, including the null. When we used inverse probability weighting to account for this education causing selection, we found more believable results, I guess, in that people tend to think that an extra year in education appears to cause a decreased likelihood of being an ever smoker or a current smoker. I think there's some caveats here around the use of Rosler in this particular example, because although obviously it did raise the year of education, it also would have had impact on where people were, as in if people who would have normally left at 15 would have been going to workplaces where at that time there would have been more prevalent smoking. I think that the instrument could have had effects on smoking that weren't just through the years of education. but through the years of being exposed to a workplace. Okay, so that's another sort of caveat for this. But to show the example, the weighting definitely made a difference. Okay. So the next bit of work I wanted to talk about again is in UK Biobank and talking about selection bias into UK Biobank. So UK Biobank, I should say up front, I think is an absolutely fantastic study. It's an incredible undertaking, and I wouldn't like the fact that I've looked at selection bias in it to be taken in any way other than academic interest. I do think it's utterly amazing what they've done. So massive study, 500,000 people, but that is only 5% of those who were invited. And there's evidence from a paper in the AJ in 2017 that, not surprisingly, biobank participants differ from the general population. So they're less likely to be obese, they're less likely to smoke. Their alcohol drinking patterns are interesting because they're different, but not in a completely monotonic way. Fewer self-reported health conditions, etc., compared to the population. So Jess Tyrrell from Exeter and a group including people from Bristol and Exeter set out to look at this in a genetic way. Now, obviously, we can't look at selection into UK Biobank using genetics until utopia, when we have genetics on everyone in the UK. But what we did look at as a kind of proxy was selection into, there's 4 optional components to Biobank at baseline. So the first one is an aid memoir. So I believe people were told some of the questions they will be asked at the baseline and asked to bring with them kind of a bit of paper to jog their memory, basically. They were asked to complete food frequency questionnaires, and we've used here the percentage of those that were completed. They were offered the chance to participate in the mental health questionnaire and to participate in physical activity monitoring. And we looked at about 80 traits, common exposures from these 8 categories, so anthropometric, behavioural, etc. And the basic choice of them, we chose ones where they had a genetic, a GWAS of a decent power, and they were in the Exeter GWAS pipeline. Okay, so they were chosen a priori, but not necessarily on grounds of whether or not they will be related to the optional component. And so what we did was, for each of the traits, we looked to see whether the genetics related to that trait were related to selection. And we also did a Mendelian randomization to see what is not quite causal, but what kind of the causal effect of the trait on selection was. I'm just going to show 2 examples. The first one is education. So the blue is the aid memoir, pink is the food frequency questionnaires, the pale blue is the mental health questionnaire, and the green is the physical activity. And you can see that those extra years of education were related to a lower chance of bringing the aid memoir with you. Maybe you just thought you could remember it, or I don't know. And higher chances of agreeing to be in the food frequency questionnaire, the mental health questionnaire, and the physical activity, wearing the accelerometer. And yeah, this one I quite liked. So there's a genetic score for risk taking, which was strongly related. If you were genetically a risk taking person, you were less likely to complete the aid memoir, presumably thinking you could take the risk of forgetting your life history. But it was fairly unrelated to completing the other parts of the optional component, although somewhat positively related to being in the physical activity, so wearing the accelerometer. So, I mean, it's kind of interesting anyway, I think, looking to see what different factors are related to those various different participation parts. But the point of it is to go back to those DAGs I showed at the beginning and to be able to start to say, for your given analysis, what is related to participation. So if you're looking at the effect of, I don't know, well, body mass index on physical activity for starters, because there's been a lot of discussion about, does body mass index affect physical activity or vice versa or both? So if you want to look at the effect of body mass index on physical activity, you will be looking at the people who agreed to be in the physical activity component. And then given this information, you can look to see whether either body mass index, or if there are inference for it, a predilection to physical activity, cause electing to be in that optional component. And that will help you to then draw that diag at the beginning and work out which analyses are likely to be biased and how. So, and generally, as we showed at the beginning, you're kind of looking to see whether your outcome causes bias or your exposure causes bias. So we're showing here, if your analysis is you want to see whether education affects risk-taking, you would draw out this little table here and say, does risk-taking affect being in these different studies? Does education affect being in these different studies? And therefore, would I expect to see a difference in my estimate if I restricted it to people who only did the aide-memoire, who answered the food frequency questionnaire, etc.? Obviously, this is a completely artificial example because we know risk-taking and education for the whole lot, but it's just to kind of show what would happen if you had to restrict to different examples because of your phenotypes. So for this one, on the left-hand side is the estimated odds ratio for risk-taking per unit change in the education polygenic risk score. So your genetic predilection for staying on at school, and what its effect is on a risk-taking behaviour, which is defined as a 1-0 sort of thing. In everybody, it's slightly positive but teeny. In those who did the aide-memoire, it's pretty much essentially the same. Food frequency questionnaire participants, it's a bit bigger. Again, mental health questionnaire participants more or less the same, and physical activity participants quite a lot bigger. I mean, well, it looks a lot bigger on this graph. The scale is still fairly small. For example, we're still talking about fairly small differences. But I guess if you were into significant values, you might conclude from the right-hand side that education increased, that there was evidence that education increased risk-taking, whereas for the results in the all category, you might well conclude that there was very little evidence that education increased risk-taking, and then the effect was tiny. Okay, so then I guess one question is, do these things specific just to biobank? So we also explored the association of genetic factors with, I've called it participation here, but it's actually dropout, because again, you can't really look at participation in a study, but we looked at the genetics of dropping out of IDSAI. And we found that, for example, the polygenic scores for higher education, agreeableness and openness, I didn't even know had genetic scores, were associated with higher participation, and various other factors such as that to do with poorer health were associated with being more likely to drop out. And I thought, quite interestingly, this shows the correlations between dropping out of IDSAI, so for mothers or for children, and participation in the different optional parts of biobank. And we did find that the aide-memoire participation was quite different from the participation in the other optional parts. I think because it's less of a participation and more a memory thing for yourself. And you can see that the aide-memoire was fairly little correlated with dropout in IDSAI, children and mothers. But the other aspects are fairly highly correlated. So it did seem that some of this selection might be very similar across at least these two studies. And I think that has quite, well, it has implications for meta-analysis, because if the same kinds of selection bias are happening in different studies, then when you meta-analyze, you're just basically narrowing the confidence intervals on an equally biased estimate, because you've got the same kind of selection bias happening across the board. Whereas if you have different selection biases in different studies, at least they would start to cancel out or appear as heterogeneity, which would be better in many ways. Yeah, and then briefly, we did the same thing in IDSAI and showed that for some analyses, there's no difference between the selected and the unselected, and then for analyses, there's quite a big difference. And I think that just gets back to the point at the beginning, is it really matters how each bit of your analysis model is related to selection for the impact it has. Okay, so the last bit is about selection in a case-only study. So here we've got exposure causes incidence of a disease, other stuff causes incidence of a disease. And what we're interested in is prognosis, which is at least in part caused by other stuff. And if we only look at people who have the disease, as you tend to do, you impose this association between the exposure and other risk factors. So it would look as though the exposure caused prognosis of the disease just because it was a risk factor for disease incidence. Now, obviously, if you knew all these other risk factors, you could condition on them and block that path, or you could do inverse probability weighting. But I guess what we're interested in is when you don't know all those other factors. And Frank Dudbridge, in a paper in Nature Communications in 2019, showed that if your genetic instrument affects an exposure that only affects incidence, your apparent effect on prognosis is proportional to the coefficient of the gene on incidence. So if you knew a load of genes that only cause incidence, and you looked at how they appeared to cause prognosis in cases, you could work out what the multiplier is to cause the bias. And then you could adjust all your biased associations in cases only and get unbiased associations, basically. So this is what he did. He plots the prognosis coefficients, the apparent prognosis coefficients in cases only against the incidence coefficients, and gets a line through them. And that is then your adjustment factor for removing the bias caused by only looking at cases. So you don't need to try and find all the unmeasured U's. It's kind of the key to this. And there's a variety of assumptions, including that everything's linear and there's no interactions and there's no really large genetic effects. But then the assumption here is that there's no so that the incidence coefficient is linearly uncorrelated with the effect on prognosis. And so then Osama Mahmood, in a paper that I worked on with him that was out this year, kind of develops a method that allows that assumption to be relaxed slightly. And the way he did this was by a cluster analysis. So basically, you only get bias for genes affecting incidence. So if we group SNPs into 4 groups, those only affecting incidence, those affecting both incidence and with a direct effect on prognosis, those affecting prognosis only, and those affecting neither. The last 2 groups are of no interest whatsoever from a bias perspective because they don't cause any bias. So we remove those using a p-value threshold, and then we use clustering to try and separate out the first group from the second. And the first group, then we can use this linear association to find the bias factor, and then we can use that to adjust the results from the second group. So you can see here the top picture shows the progression coefficients against the incidence coefficients. And here we've taken out with the p-value threshold the ones that don't affect incidence. And then we've separated them by clustering into a group that lie very closely along a line and those that lie further from the line. And that line then is our bias adjustment. And we use that to adjust the values of all these grey ones to show their true effect on prognosis. Just a brief example here, which is from the paper, which shows the effect of adjusting 3 alleles that are related to breast cancer risk. You've got their association with breast cancer risk here, their association with mortality in breast cancer cases only, and then that adjusted using this particular method. So you can see here that if it's not related to breast cancer risk in the first place, then adjusting doesn't have much effect, because if something isn't affecting incidence, then it can't suffer from collider bias due to selecting only cases. And with the second 2, they'd shown this slightly paradoxical thing where this one was protective for breast cancer, but appeared to increase mortality. And this one was a risk factor for breast cancer, but appeared to have no effect on mortality. And the adjustment made them arguably more plausible, but obviously it's an applied example, so we don't know the right answer. So here, this has the same assumptions as the Dudbridge method, but we assume that at least 50% of the SNPs that affect incidence only affect incidence, which again is quite a large assumption and one that we can't prove. So this is really an area of ongoing research. And my last slide, I guess a question, a sort of crucial, more philosophical question, I guess, is what are we estimating at this point? And I think I've heard this discussed a lot, where, for example, you have a randomized trial where people have died before the end of follow-up, and you try to get rid of the bias due to survivor bias. But then you can be estimating some really odd things, like what would the effect of the treatment be if somehow you'd magically prevented everyone from dying? And I think here we're doing something very similar. We're saying, what would be the effect of this exposure on prognosis if we'd given everyone the disease, irrespective of their exposure? They've been forced to have the disease. And so again, I think there's some work to be done thinking about what that means and whether we can estimate things that are of more obvious applicability. So I feel like it's been quite a whistle-stop tour, and I certainly need a drink now, but yeah, I have this long-held fascination by collider bias and selection bias. It can, like I say, selection into a study, drop out from a study, studies of prognosis. And I think the increased use of DAGs to really draw out what your underlying assumptions are and how they might impact this has been one of the developments of the last sort of 10 years. I think really has changed the way we think. And yeah, hopefully this is some tiny part in that. And thank you very much.
Fantastic. Thank you very much, Kate. You can stop sharing now. I'm going to stop the recording so that we can have some questions. If